Deep in the vast expanse of the cosmos, nearly 4 billion light-years away, lies a remarkable cosmic spectacle known as the Bullet Cluster. This celestial object, officially designated as 1E0657-558, bears witness to a titanic clash between two enormous galaxy clusters. These clusters, each containing hundreds of galaxies, collided at incredible speeds, creating a cosmic train wreck of epic proportions. The Bullet Cluster provides astrophysicists with a unique natural laboratory to study the invisible universe, particularly the elusive nature of dark matter. Located in the constellation Carina, it is one of the most energetic events ever observed in the universe. The collision between the two clusters offers valuable insights into the distribution and behavior of matter, both visible and invisible. By studying the aftermath of this cosmic event, scientists hope to unlock the secrets of dark matter and its role in the evolution of the universe. The collision between the two galaxy clusters in the Bullet Cluster was not a head-on smash-up. Instead, the clusters grazed each other at an oblique angle. This glancing blow created a shockwave that rippled through the clusters, heating the intergalactic gas to millions of degrees. The intense heat caused the gas to emit X-rays, making it visible to space-based telescopes. However, the most intriguing aspect of the Bullet Cluster lies not in the visible matter, but in the unseen. As the two clusters collided, their constituent galaxies, stars, and planets interacted gravitationally. This interaction disrupted the original trajectories of these celestial objects, scattering them across a wider region of space. The intergalactic gas, being more diffuse, experienced a different fate. It collided directly with the gas from the other cluster, creating a drag force that slowed it down. This separation of the gas and the galaxies provided the first crucial clue to the presence of dark matter. Scientists used NASA's Chandra X-ray Observatory to study the hot gas in the Bullet Cluster. The observatory detected a bright X-ray glow emanating from the region where the two clusters collided. This glow confirmed the presence of superheated gas, heated to millions of degrees by the shock wave. By analyzing the intensity and distribution of the X-ray emissions, astronomers were able to map the distribution of normal matter, primarily in the form of hot gas, in the Bullet Cluster. The X-ray observations revealed that the bulk of the normal matter in the Bullet Cluster was concentrated in the center, where the two clusters had collided. This finding was consistent with the expected behavior of gas during a collision. The gas, being more easily affected by electromagnetic forces, would have interacted strongly, leading to its deceleration and concentration in the central region. However, the distribution of mass, as inferred from the gravitational lensing observations, told a different story. To determine the total mass distribution in the Bullet Cluster, astronomers turned to a technique called gravitational lensing. This technique relies on the fact that massive objects, such as galaxy clusters, can bend the path of light traveling through them. This bending of light, predicted by Einstein's theory of general relativity, acts like a cosmic lens, distorting the images of background galaxies. By analyzing the distorted images, astronomers can map the distribution of mass in the lensing object, even if that mass is invisible. When astronomers applied gravitational lensing to the Bullet Cluster, they found something astonishing. The regions of strongest gravitational lensing, indicating the highest concentrations of mass, did not coincide with the hot gas observed in X-rays. Instead, the mass was concentrated in two distinct regions, flanking the central gas cloud. These regions corresponded precisely to the locations of the two galaxy clusters, as if something massive had passed through the collision relatively unscathed. This invisible mass component, dubbed dark matter, provided the most compelling evidence to date for its existence.